Hi everyone! In this video, we will compare different ways to tell a transformer model where each word appears in a sentence. This is called positional encoding. Why do we need positional encoding at all? Let's look at an example. Imagine we take this sentence and break it into individual tokens like this and turn each token into an embedding. Here is the embedding vector for the word high. Without positional encoding, the same vector is used no matter where high appears in the sentence. That's a problem because the self-attention layer needs to understand word order. That's why we need to add positional information. But how we do that? There are a few ways to add positional information. The main types are absolute positional encoding and relative positional encoding. Let's go back to our example. We have the embedding tensor and the positional encoding tensor. We simply add them before sending them to the self-attention layer. So, how do we actually build this positional encoding tensor? This is what we are going to see in this video. Let's start with absolute positional encoding. There are two main types. The first one is learnable positional encoding. In this method, we add a special tensor of weights, which is going to be learned during training, one for each position. So here is the matrix, or here are the weights that are going to be added to the transformer model. And as you can see here, we have positions, and this can handle up to block size. So during training, we are going to learn each position individually. And here you can see that we have the embedding size. So this is the shape of the matrix. The shape is the max length, which is block size, by embedding size. During training, the model learns what values work best for each position. At the end, we get a tensor, let's call it WF, which means the final weights, that contains all the positional vectors. But this method has a key limitation. It does not generalize to longer sequences than what it was trained on. And in this case, it's block size. So if you decide to use sentences that are longer than block size, this method will not work. Another issue is that each position is learned independently. So the model does not know that position 5 comes before position 20 because there is no relationship between them. If you shuffle the tokens in the input sequence, the model won't notice anything is wrong. That's a weakness of this approach. Next, we have sinusoidal positional encoding. Instead of learning position vectors, we use mathematical formulas, sine and cosine waves, with different frequencies. As you can see, here are the formulas we use to generate them. This method was used in the original transformer paper. Because it is formula-based, we don't need to learn anything. And we can handle inputs longer than what the model saw during training. Because we have just two formulas and we can just pass the values and we will get the positional encoding for that specific position. Here is how this method works. We build a tensor shaped max length by embedding size, like what we have seen before. And here, let's just focus on the 20th position. We apply the formulas that I have showed you in the previous slide for each dimension of the embedding. Here is what the wave plot looks like. The x-axis is the position, and the y-axis is the embedding dimension. At position 20, we sample values from all the waves. And just like that, we create our positional vector. If you want to get the vector at position, let's say 60, you come here, you intersect these waves and you get the values. And just like that, you construct the positional vector at that specific position. That's it for absolute methods. Let's move on to relative positional encoding. Instead of focusing on where each token is in the sentence, this method cares about how far apart tokens are from each other. This method does not modify the embedding itself. Instead, it changes how self-attention works by including information about the distance between tokens. For example, if we are attending from the token high, if we are attending from the word high, the token Imad might be one step away and the token Najma 3 steps away. And this number basically means the distance between the token high and the other token. You can see that the distance between high and high is 0 because it's the same token, but the other ones that come after have positive distance. But in the other case, let's take the second high. You can see that this one will have a distance of 0, but the ones that come before it will have a negative distance, and the ones that come after it will have a positive distance. What's cool is that nearby words or tokens have more influence and distance ones have less influence, just like how natural language works. So this is how relative positional encoding works, and it's, as you saw, it's different from absolute positional encoding. Now let's talk about rotary positional embedding. This method combines the best of both worlds. It captures both absolute and relative positions. It does this by rotating token embeddings in space. Imagine our embedding space is two-dimensional. Let's say that the token Imad is located here. Now we add a token before it. Let's say that we added high. Now rope, this method, will rotate the token Imad by a fixed angle, theta, for each new token added before it. So if the token Imad is the second token in the sequence, rope will rotate it by one angle. If it is, in this case, located at the fifth position, so 1, 2, 3, 4, 5, rope will rotate it by 4 theta. And theta is just the rotation angle. So yeah, this is how this method works. And also, what's amazing about rope is that it preserves the relative angle between tokens. Let's look at this sentence. My friend is Imad. The angle between the tokens friend and Imad is represented here, represents their relationship. So let's say that we changed that sentence to this one. Who is your friend? My friend is Imad. You can see that because here we added tokens before this sentence, we need to rotate these tokens. And as you can see, the angle between them is preserved. And just like that, rope preserves relative positions even if the sentence structure changes. Here are some great resources I used to learn these different positional encoding methods. You have Jake's blog on relative positional encoding, this YouTube channel that explains rotary positional encoding. I highly recommend this video. It is really great. Christopher's Hugging Face blog on positional encoding, and my own GitHub repository. Here I try to keep updating the resources file with the new links that I find useful. Here it is if you are wondering about it. So just click on the resources and you'll find the useful resources there. Now that we have seen all the methods, let's test them. I will train a small model using the AtlasSet dataset, and to save time, I will only train for one epoch for each method. So here are the methods that we are going to test. So we are going to test no positional encoding, absolute, relative, sinusoidal, and rotary positional encoding. After each run, I will save the training and validation losses so we can compare them. Let's start with no positional encoding. This one is easy. Let me show you the diagram. We just remove the positional encoding layer from our transformer. So you can see that here is the sentence that we convert into individual tokens. We get the embedding, so the word embedding, and then before we used to compute the positional encoding and add the two tensors. In this method, we are going to remove this part from the transformer architecture and do the training. So you can see that here I say that don't add positional encoding to the embedding tensor. So this should be removed. Let's look at the code in VS Code. In the previous course, we used this script, model.py, to create our GPT class, or this one, so GPT language model. I have just copied this script and created a new one that I called model no positional encoding. And let me show you the difference. This one is, it's not that hard to understand. So here you can see that before we had two embedding tables, one for the token embedding and the other one for position embedding. In the forward pass, you can see that we take the input. So here are the input tokens that we got from the input sequence. We pass that to the token embedding and positional embedding. After that, to get the input that will go into the blocks, we take the token embedding and add to it the positional embedding. Now, look here in model no positional encoding, you can see that I have removed the positional embedding table, and in the forward pass, I take the input tokens, I pass that to the embedding table, and I create my input. So you can see that this is the only change. Just remove the positional embedding and take the token embedding and consider that as the input. Okay, so after doing this, I have created a notebook to test this. So it's this one, no positional encoding. And again, this notebook, I just took one of the previous notebooks in the previous course that I used to do pre-training. And this is the only change. So instead of importing the GPT language model class from model, I am importing it from this new script. And also I have made sure to tweak these parameters so that I get a small model, because I will be doing a lot of experiments and I don't want this to take me a lot of time. So I want to test this on a small model just to confirm that these methods work. And then once you will see in the end of this video, once we get the method that works well, then we are going to increase the size of the model and use it. But this time, because we are just doing a lot of experiments, we want to do it on a small model. I have also changed one thing, which is the evaluation method. So here we have this estimate loss method that we call periodically during the training loop. But before, in the previous course, I used to take random batches for evaluation. This time I have changed this method to use the same batch each time, so we can track improvement clearly. And this is how I have done that. So you can see that here I have this. So we have evaluation batches, which is set to 1000 batch. You can change this value if you like. The more, the better. Here I have get evaluation indices, and this one works both for training and validation. And here you can see that I compute this only once and then I reuse it. So evaluation indices, this dictionary will contain the batches for training and validation. And here you can see that we are getting them randomly, but only once. But later, when I call estimate loss and use the get batch for loss estimation, you can see that here I am using evaluation indices, and I am providing those indices to the get batch for loss estimation. This allows me to get the same batches during evaluation, and it will show us if the model is learning, is improving during training or not. Also, let's go down. So here is the training loop. Here I have also added a learning rate scheduler. I have used cosine annealing learning rate with warm-up. So why we use cosine, not just cosine, but why do we use learning rate schedulers in general? Basically, before we during training, we set the learning rate to a fixed value, let's say 1e minus 4. And that value will be used during training. It will not change. Learning rate schedulers allow you to change that value dynamically based on the number of epochs or the number of iterations. So here we are using cosine annealing learning rate scheduler with warm-up. What does it mean? So here you can see that we are computing the warm-up iterations. Now warm-up will take the learning rate and keep increasing it until we reach this number of iterations. And later it will start decreasing. Here is an image that I found that explains it. So you can see that this is the warm-up phase. The learning rate starts from a minimum value and goes to a maximum value. Then it starts decreasing following a cosine wave. And this is exactly what we have in the code. So we have the warm-up iterations, which is the first phase of this scheduler. And after the warm-up phase, we are going to use this scheduler to decay the learning rate and until it reaches this minimum learning rate value. So yeah, this is something that I have added to the training loop. And yeah, these are the only changes that I have made, and everything stayed the same. So after training, so I have already done the training, and I have saved the training and validation losses. And now let's go back to the slides to show you what we got. I am back, and here is the plot. So you can see that here we have two curves. So we have the training loss and validation loss. And here I have used no positional encoding. And as you can see, the loss was going down, but then it stagnated, which means that the model is underfitting. And this is probably because the model is small. But we don't care about this. We want to compare the methods. So this is the first one. We have the graphs. Now we are going to go to and before that, I just want to mention the training time. So for one epoch, the model took roughly 2 hours to train. The next method is absolute positional encoding, and we are going to focus on the learnable version. This is the one we used in the previous course, so no code changes are needed. You saw in VS Code that we have a script called model.py, and we are going to use that one. So I will not go to VS Code, I will directly show you the results and compare this method to the no positional encoding. So here we have two graphs, one for the training loss and the other one for the validation loss. The orange line is absolute positional encoding and the blue line is the no positional encoding method. And as you can see in both graphs, the absolute positional encoding method performs better than no positional encoding. And this was expected because, as I said, adding more information to the transformer helps it to learn better. And again, the training time, so this method also took roughly 2 hours and 10 minutes. So there is no difference in training time. I am keeping track of the training time because this is something that we need to take into consideration, because if we get two methods that work, that give us the same performance, but one takes more time to train, then this will help us choose which method to keep. Now we are looking at sinusoidal positional encoding. This is another way to add positional information to tokens. This method is pretty interesting. On paper, it should perform just as well as the learnable version, but it does not have any learnable parameters. So if it performs like the previous method, which is absolute positional encoding with learnable parameters, this will be good because it will save us parameters. Let's see how this one is implemented in code. Okay, so I will remove this, script, and I have another one which is called model sinusoidal positional encoding. I will put it here, and let me scroll until I find the GPT language model class. So as you can see, we don't have the embedding table for positions. So this means that we remove those parameters from the model, but here I have added positional encoding. So this method will compute the positional encoding up to block size. And let me go back to that method. Also, I need some space. Okay, great. So you can see that here, create sinusoidal encoding will use the two formulas that I have showed you in the slides. It will use the sine function and cos function to compute the positional encodings. And this, the implementation that I have here, basically will just use those functions. So yeah, as you can see here, we have that 10,000 value that I have showed you in the slides. And yeah, we are going to, the sine wave is used for the even positions, and the cosine value is used for the odd positions. And at the end, we will get a positional encoding tensor of shape 1 by max length by embedding size. And we compute these values only once. So when we instantiate a new instance of the GPT language model class inside the constructor, we are going to call that method and store those positional encodings in this buffer that we called positional encoding, and later we are just going to use them. So this is the difference between sinusoidal positional encoding and absolute positional encoding with learned parameters. Here we have 0 parameters that we add, but we compute the values beforehand so that we use them later. Okay, so here is the sinusoidal encoding. And now where do we use them? So you can see that here in the forward pass, again, we did the same thing. So we take the input tokens, we pass them through the embedding table. This gives us the token embedding. And here I try to add the shapes because when creating a model, this is the most important thing to look at. So the shapes are very important. And after that, we get the positional encoding. And remember, where do we get this? Because we have that stored in this buffer, we have access to this variable or to this tensor. And here we need to take just a slice. If we have a sequence that has just 10 tokens, we are going to take just the first 10 values from this tensor, or the first 10 vectors from the tensor. We don't want to go up to block size. So we get the positional encoding and we add that to the token embedding tensor to get the inputs that will go to the next layers in the transformer. After that, I have done the same thing. I have this notebook improving the transformer sinusoidal positional encoding. Inside, I have done the same thing. I have made the model small, so the size is just 11 million parameters. I have made sure to change the way we evaluate the model, and I have added the learning rate scheduler. And I have run this, I have saved the training and validation losses, and I have created the graph to compare the 3 methods. So let's go to the slides and let's see if this one performed well or not. Here are the graphs, and again we are comparing the sinusoidal positional encoding to the other ones in both training and validation. Surprisingly, this method performed worse than both other methods on both training and validation. So you can see that in some cases, so here the gap is a little bit small between sinusoidal and no positional encoding, but during training the gap is a little bit bigger. So this means that using learnable parameters is better than just pre-computing those with the sine and cosine formulas that we have seen. Okay, let's move on. Before that, I always forget to mention the training time. Also, this one took 2 hours and 10 minutes. Next up, we have relative positional encoding. There are a few versions of this method, but I will show you the one with learnable parameters. Here is the idea. We define a range of relative distances with this parameter max relative distance. Let's say if this parameter is set to 8, we will have 2 distances. We will have negative distances and positive distances. This is what we have seen before. because the tokens that come before the token will have negative distances, and the ones that have positive distances, or the ones that come after the token, will have positive distances. And that range is called a number of buckets. Let's show you an example so that you can understand. So let's take this sentence. So here we have maybe we have other tokens that come before, and here maybe we have tokens that come after. Let's say that max relative distance is set to 4, and let's take the word or the token not in this sentence. So here I said that we will have positive distances, and we will go up to max relative distance, which in this case is set to 4, and we have negative distances. So this range is called the number of buckets, and it contains unique learned bias values. So this is the range that we are interested in, because as I said before, tokens that are very close to the one that we are looking at will influence it more than far away tokens. So tokens that are very far away, that have very big distances, should not affect the token very much. Now, what do we do with the tokens that are outside this range? These ones will have shared biases. What bias do we take? So let's take the tokens that are on the left. These ones will use the first value from the unique learned bias values. And the ones that are here on the far right will use the last value from this range. This way, the model does not learn absolute positions, but learns how far apart two tokens are. Since this method is a little bit tricky to implement, I decided to make this diagram to help explain how the model uses this method. The diagram looks a little bit scary because it's big, but I'll try to make sure to explain each part individually so that you can understand the full picture. We start with a sentence. In this case, this sentence is, "Hi Imad, how are you doing?" We split it into individual tokens. Here we have 6 tokens and 1 sentence. This is the input shape. 1 is the batch size, and 6 is the number of tokens in the sequence. So after doing this operation, we are going to pass this tensor into the token embedding table. After that, we get a tensor of size 1 by 6 by 768. 768 is the embedding size. And here the block size is set to 1024. So this is the input. Now we need to feed this tensor to the attention layer. Here we have 2 individual parts. The first one is the multi-head attention layer, and the second one is the layer where we are going to compute the relative bias that will be used after. But let's focus on the multi-head attention layer, because I don't want to show a lot of heads because the diagram will be too complex. I have decided to show just 2 heads, and everything is explained in the first head, but the second one is, I don't show a lot of information because it's the same thing. When we take this input tensor and feed it to the head, we are going to create 2 tensors of the same size. So we have the key tensors and the query tensors. And here I said that we will create a tensor of the same size, but here you can see that the shape is not the same. So here we have 1 by 6 by 384. So 384 is just this value divided by the number of heads. Since we have 2 heads, we will divide 768 by 2. This will give us 384. So we create these 2 tensors, k and q. We transpose k to get this tensor. So the shape is 1 by 384 by 6. After that, we multiply these 2 tensors, and at the end we get a tensor of size 1 by 6 by 6. We do the same thing for the second head, and we stop here. We don't continue. We go back to the layer where we calculate the relative bias and do this. First, we create 2 position vectors, one for queries and the other one for keys. And here the size is 6. So we have 1 as the batch size and 6 is the number of tokens. So we take these two tensors and we use broadcasting to compute a 6 by 6 matrix. I think this is too small, so let me go back to Inkscape where I created this diagram and zoom in so that you can see this clearly. Okay, so this is Inkscape, and now I think you can see clearly. So I said we start with two tensors, one for query and one for keys. We use broadcasting to compute a 6 by 6 matrix from these two tensors, and this one is called relative positions because this matrix will have the relative distances between every pair of tokens. The diagonal contains zeros. The upper triangle of the tensor contains positive distances, and the lower triangle contains negative distances. Now we take this relative positions tensor and we shift it and clamp it. Here I am not showing a lot of detail, but don't worry, when we are going to switch to VS Code, I will show you everything that goes under the hood. After clamping, we are going to have values between 0 and a maximum value. That maximum value will be the number of buckets minus 1, but as I said, I'll not go into details. Why are we clamping the tensor? Because we cannot use negative values to get vectors from the embedding table. This will give us an error. So we need to have positive values to do that. So we take the values from here, we get the vectors from the embedded table, and we create this tensor. You can see that the shape here is number of heads by 6 by 6. This is very important because if I go back to the multi-head attention layer, you can see that the input is 6 by 6. And because we have two outputs, the shape should be number of heads, which is 2 by 6 by 6. So this matches what we have up here. Now we take each slice and we add it to the output of each head. So let's take this slice as an example. And here we take this tensor, we add them together, and the output should stay the same. It should be 6 by 6. After that, we continue. From X, we get the value tensor. We multiply these two together. We get the final attention weights. We do the same thing for the second head. We concatenate the results. And as you can see, we are back. And here, outputs and X have the same shape. So this is how relative positional encoding is implemented. I hope that this diagram was helpful, and now let's go to VS Code to see how to turn this into code. Here is the same diagram. I'll keep it here because I need to explain to you how this works. And instead of model, I have another script called model relative positional encoding. Let me put this one here. So I'll make this a little bit smaller. I hope it's not too small. And now let's go down. Here is our class. I added a new parameter to the model, max relative distance. We pass it from the GPT language model class to the block. After that, inside the block, we pass it to the multi-head attention layer. And here we start implementing the relative positional encoding. First, we start with number of buckets. Number of buckets is 2 times the relative distance. Remember, why are we multiplying this with 2? Because we have positive and negative distances, and we add 1 to take into consideration the distance 0, because if you are looking at the same token, the distance should be 0. So this is the range. I call this in the slides unique bias values. And after that, we create the relative attention bias embedding table with shape, number of heads by number of buckets. And it's this one. Let me zoom in a little bit. So you can see that here, this is exactly what I have here in the code. You can see that here we have number of heads and number of buckets. Currently, we haven't done any calculations. So let's back up. Here, I need to go inside the forward pass. So here I am going to start with relative bias calculation. Here I am going to get the relative bias, which is basically this yellow tensor or this green tensor. So I have this compute relative position bias method that I am going to use. And here you can see that let me zoom in again. We have two tensors, query positions and key positions. Here they are. And we are going to have a tensor of shape 1 by sequence length or batch size by sequence length. Okay, so we have query and positions. This is how we create the relative positions. So the shape will be t by t. Here it was 6 by 6, but in general it should be sequence length by sequence length. And here is how we do that just by using broadcasting. So we take key positions and we subtract key query positions. If you don't understand this notation, don't worry, I will show you how this works. So I will open my terminal. Here I will type Python. Let's start from the beginning. Let's import PyTorch. Here the sequence length is set to 4. This is just an example just to show you how this works. I will also create the key tensor and query tensor. So let's look at them. Key positions. This is the content of key positions and key query positions. Now let's run this code, relative position. So let's look at relative position. As I have mentioned here, the diagonal should have zeros. That's what we have here. The upper triangle contains positive distances. Here they are. And the lower triangle contains negative distances. Now I said that after computing this relative position tensor, we need to shift it and clamp it. So this is the first operation, which is shift the range to positive values between 0 and 2 times max relative distance. And this is how we do it. We take relative position and we add to it the max relative distance. And in this case, max relative position, it's not defined. We should pass it when we create the model, but let's just add it here. Let's say that max relative distance is, maybe we want to look at just two tokens, before and after the token that we are looking at. And we are going to take that. So let's take relative distances and we are going to add to it this value, max relative distance. So it tells me that relative index is not defined. That's correct. Let's create it again. Relative indices is equal to relative position plus max relative distance. Now let's look at both tensors, relative position and relative indices. And as you can see, things are shifted. So max relative distance is equal to 2. So the diagonal before was 0, now it is 2. So basically we added 2 to every value in this tensor. But we need to clamp it. So this is the second operation. And here is how we do that. So let me take this. And as you can see, here we no longer have negative values. Let me show you how relative indices was before. Relative indices. You can see that in this position, we have -1. After clamping that tensor, we have 0. And here we had 5. And because this is the max value, which is here 5 minus 1, which is 4, this value was clamped to 4. Why are we doing this? Again, just to remind you, because after that, we are going to take these values and try to get the embedding vectors from this embedding table. And we should not, because here, this is these are the positions. So buckets goes from 0 up to number of buckets -1. And here, if, for example, if you try to get a vector at position -1, you will get an error. Or if you try to get a vector at a position higher than the maximum position, you will get another error. This is why we need to do this operation, shift and clamp. Okay, so now we have the relative indices. Now we are going to use that table, that embedding table, to get the biases, and we are going to permute the dimensions, because this gives us t by t by number of heads. And as you can see from the output, we need to change that to be number of heads by t by t. So we do that with the permute method, and you can see that here 2 is basically number of heads. We put that at the first position, and we put t by t at the last positions. After that, we return that bias. This means that we return this. Okay, so here they are. So relative bias is this tensor. Now we loop over the heads, and for each head, we take one slice from this tensor. It's this arrow that goes here. We take one slice and give that to the head. Now let's go to the head class to show you how that works. So here is the head class. Inside the forward pass, we get the input, which is this one, X, and we get the head bias, which is one slice that we get from this tensor. Okay, so now let's look at head one. You can see that we get key and query from the input X. We transpose the key tensor and we multiply it. Here we are using matrix multiplication. We multiply it by Q in order to get the weights. Here they are. Now, before continuing, we are going to take that slice. It's here. We got it from the previous step. So we are going to take that weights tensor and add to it the head bias. And here we are using unsqueeze because head bias is going to be T by T. And we need to add the batch dimension so that broadcasting works. So after doing this, we are going to continue like before. We are going to have to use maxed fill so that we only keep the lower triangle in the tensor. After that, we apply softmax, dropout, etc. And then we come to this part. So we get the value tensor and we multiply it by the weights in order to get the output from one head. And after that, we just concatenate the results. And this is done in the multi-head attention class. So at the end, let's go here in the forward pass. This is where we were. So for each head, we take one slice from this tensor. We get the head output, which is this one. We append everything, but at the end, we concatenate those tensors in order to get the output. In this case, it will be of shape batch size by sequence length by embedding size, which is similar to the input tensor. So yeah, this is how you implement relative positional encoding. And again, I have created another notebook to, let's look at it, relative positional encoding, this one, to use this method and to get the training and validation losses. Now, let's look at the results in the slides. Okay, so I have explained everything here. Okay, so relative positional encoding. Again, we have training and validation, and you can see that relative positional encoding performed really well on both training and validation. So you can see relative positional encoding is this one. It has this plus icon or plus marker. But the downside is that it is slow, because you saw we have a lot of calculation performed under the hood. It took 5 hours, and if you remember, the previous method took 2 hours to train. But it is worth it because we got so far the best performance. Now, we have one more method before we end this video, which is rotary positional encoding. So let's look at that. This method does not add any new parameters. That's a good start. Instead, it modifies the key and query vectors by rotating them before calculating the attention. I took the previous diagram and made it a little bit simpler, or I have adjusted it to work for rope. And I think this is a great idea to explain how the method works under the hood instead of just showing you the code. So let's start. How does this work? You can see that here, the only thing that you need to change is this. When you create the key and query tensors from the inputs, you will rotate them before calculating the attention weights. So when we are going to go to VS Code, we are going to focus on this part. So don't care about the other parts, just look at this one. You can see that here, this icon means that we are going to rotate that tensor. Let's go to VS Code and let's search for model rope. Okay, let's go down to the GPT language class. You can see that I have added a new parameter called rope base frequency. It is equal to 10,000. I took this from the raw former paper. So they are using this to compute the frequencies. We are going to look at this later. And here you can see that I have also added this Rotary positional embedding class, which will compute those embeddings or those frequencies. And we pass that to the block. We will do the same thing as relative positional encoding. Later, we are going to pass it to the multi-head attention layer. But before looking at the block, let's understand what is happening inside this class. Okay, so in the init function, you should understand that the rotary positional encoding method treats pairs of numbers as complex numbers. This is why we are going to loop from 0 up to embedding size divided by 2, because we are going to take two values from the embedding dimension and consider them as one complex number. Now, each frequency value is calculated like this. So you have theta at index I, so it's equal to 1 divided by the base frequency, which is equal to 10,000, but you can change that when you create the instance. So yeah, this method or this formula was taken directly from the raw former paper. And here, this is just a code to basically calculate this. And so yeah, as you can see, this one divided by the denominator, which is, yeah, it is calculated here. Okay, so after getting the theta e's, we are going to multiply those values with the position indices. So position indices, again, will go up to block size. And here we are going to use torch.outer to get the frequencies. Now, if you don't understand what torch.outer does, let me again open the terminal, and here I will create two tensors just to demonstrate how that method works. Okay, so we have tensor A and tensor B. Now I am going to write torch.outer, and I'm going to pass A and B. And here is the output. Let's see how this first row was calculated. So you take 1 and multiply it by these values. So 1 times 4 will give you 4, 1 times 5 will give you 5, etc. Now to compute the second row, we take 2 and multiply it by these values. So 2 times 4 gives you 8, 10, etc. So this is how torch.outer works. Now let's go back to the code. Okay, so here we have two tensors. So A and B in this example are position indices and theta e's. And here, the vectors don't need to have the same shape. So if I go back to A, and instead of 1, 2, 3, I will just remove 3. Let's go back to torch.outer, and as you can see, that works. Here we have the same things. So position indices will be of shape batch size by block size, and theta is of shape batch size by embedding size divided by 2. So when we use torch.outer, we are going to get a tensor of size, block size by embedding size divided by 2. And this will give us the frequencies, and this is what we need. Now from this, we are going to calculate the complex numbers in polar form. This is the polar form. So cos m theta plus I sine theta. And torch.polar will do that for us. We will get theta e's, and this is what we want. So theta e's are computed only once when we create an instance of the GPT language model class. And this is similar to the sinusoidal positional encoding. There we used the sine and cosine formulas to calculate those positional encoding only once. But here we are computing these frequencies or these values that are called theta e's, each position only once. And we have a method which is called get theta e's to retrieve them later. So this was too much math, I know, but as I said, this was taken directly from the raw former paper, but I wanted to show you that this exists in this script so we can look at it. And to understand, try to make examples like this with smaller numbers, with smaller shapes, to understand how does the math work. And yeah, because when creating any deep learning model, shapes are the things that are going to cause you a lot of trouble. You need to either do this by pen or paper, or open the terminal and try to create the tensors manually, see how the shapes work, and this will help you understand any deep learning model that was implemented by someone, or it will also help you create any deep learning model. This is the role of rotary positional embedding. Let's go back to GPT language model. I have it here, and then I pass it to the block class. So inside block, we pass it again to the multi-head attention layer. Here, inside the head, we get the key and query tensors from the input X. And again, just to show you where we are in this diagram, let's make this a little bit smaller. Let's zoom in a little bit. You can see that we are here. We got the key and query tensors. Now we need to rotate them. I have added this helper function, apply rotary positional embedding. So it takes the tensors, it takes the theta e's, and it will rotate those tensors. And after that, the rest is the same. So you get Q and K, you transpose K, you multiply it by Q, you get the attention layers, you apply the mask, you apply the softmax dropout, and finally you multiply this by V and you get the attention weights at the end. So the rest is the same. This is the interesting part. So apply rotary positional embedding. This is a function that I have outside that will do this rotation for us. The tensor X has this shape, batch size by sequence length by embedding size. We take it and we reshape it to be of shape b by t by d over 2 by 2. Why are we doing this? Because remember, when we computed theta e's, I told you that rope will divide the embedding size into 2 and consider each pair as a complex number. This is exactly what we have done. We have divided the embedding size by 2 and we created a new dimension. Now, after that, so this will give us x combined. We will convert this into a complex number. And now we will have b by t by d over 2. And this dimension will go because we are going to create the complex numbers. Again, if you don't understand how this works, you can come here and create a tensor. So let's do that. Okay, let's look at the shape. So it's 2 by 2. And I will unsqueeze it to add the batch size or the batch dimension. So now, so I need to type x equals x dot unsqueeze. Now x dot shape should be 1 by 2 by 2. So this is exactly what we have here. Now we need to reshape this. So let's take this. Now let's look at x combined. Let's look at the shape. And it's 1 by 2 by 1 by 2. So let's use this function. Let's put it here. And as you can see, let's look at the shape. So it's 1 by 2 by d over 2, which in this case is 1. And as you can see, we have complex numbers. So this is the real part, and this is the imaginary part of that complex number. Okay, so now we got theta e's. So they are here. Theta e's are complex numbers, so pre-computed complex frequencies of shape t by d over 2. You can see that here we are missing the batch dimension. This is why I used unsqueeze. And now the shape should be 1 by t by d over 2. Now we need to apply the rotation by multiplying complex numbers. So we do this by just a simple multiplication. So here x complex has this shape, theta e's has this shape. Broadcasting will work. And this will give us a tensor of this shape. So it's the same shape, but this will result in rotating that tensor in the complex plane. Now we need to go back to real numbers. So torch.view as real will give us that dimension back. And now we need to flatten the shape to combine these into one dimension. So you can see that here, flatten the last two dimensions to get the embedding size back. So at the end, x out will have this shape, b by t by d. And this is exactly what we have here. So the input was 1 by 6 by 384. After rotating the tensor, it should stay the same. Okay, so here the input was b by t by d. So the output should be b by t by d. And that's it. This is how you implement rope in Python. Again, I have created another notebook to do the experiment. So it's this one, transformer, where is it? Yeah, it's this one. So improving transformer rotary positional encoding. I'll make sure to clean everything because here I have created a lot of files. So I'll make sure to clean them and then push everything into my GitHub repository. In that notebook, again, I created the model. I have used this script to instantiate the GPT language model class, and I have the results. So let's go back to the slides to show you what we got. Okay, this is the slide. So now I am comparing all the methods. So we have absolute, no positional encoding, sinusoidal, relative, and finally rope. And as you can see, rope is this one. It's in yellow. And as you can see here, it was close to the relative positional encoding method in terms of the loss value at the last iteration. But here you can see during the validation, it's performed better. So both of these methods are really great. So relative encoding and rope are the best, but since rope took 2 hours to train, and if you remember, relative positional encoding took 5 hours to train, this means that this method, rope, is 2.5 times faster than relative positional encoding, and also it generalized really well. And this is shown by the lower validation loss. So this means that we are going to consider rope as the winner in this experiment that I have conducted in this video, just to show you that positional encoding is very important. So if we decide to not use positional encoding, we will get this blue line. So the loss will be here, and the same for validation. But just by adding positional encoding, we improved the performance of the model by a big margin. So you can see the gap between no positional encoding and Rotary is very big. And the same for validation. So this means that, yes, positional encoding is very important. Yes, we have a lot of methods, and we compared between them, and we ended up choosing Rotary positional encoding because it is faster and it generalizes well in validation. So yeah, this is the method that I am going to keep, and it is going to be used in the final version of the model in the final video. I hope you found this first video in this course helpful. It took a lot of time to make, so if you learned something, let me know, and see you in the next video.